Big news, Eons fans! We made a TV show. Eons, Life and Death on Pangaea is our most ambitious project yet, and is now available. Check out the link in the description for details, and we'll tell you more later in the episode.
The extinction at the end of the Permian period was among our planet's darkest hours. A colossal volcanic eruption spewed out greenhouse gases. Temperatures skyrocketed. Oceans were robbed of oxygen and acidified, and toxic gases smothered the surface of the Earth. Ecosystems collapsed, and the vast majority of species were wiped from the face of the planet. But for the smallest among us, the story went very differently. As larger life was decimated, microbes began to thrive. Thick mats of slime spread across lakes, rivers, and along the coasts of the oceans. For 3 million years, microbes ruled the Earth. But were these tiny survivors just lucky? Or did they play a more sinister role in the greatest disaster our planet has ever faced? Turns out, microbes, metal, and methane might be a lethal combination. Around 300 million years ago, dense forests covered the southern half of the supercontinent Pangaea, what is now South America, Africa, India, Antarctica, and Oceania. Broadleaf trees called glossopterids reached as high as 30 meters. Beneath them, lush swamps provided a home for amphibians, reptiles, and the ancestors of mammals. The remnants of all this life can be seen to this day. It's carbon preserved in Permian-age coal beds. But to the north, beneath what is now Siberia, trouble was brewing. A gigantic plume of hot material was rising up through the mantle. And around 250 million years ago, it reached the surface, cracking the ground open and spewing out 4 million cubic kilometers of lava. The Siberian traps covered an area nearly 3/4 the size of the United States. The rich ecosystems of the Permian came crashing down in the most devastating mass extinction in our planet's history. In the oceans, life struggled to hold on, and over 80% of species weren't able to. It was the end for the famous trilobites and 2 out of 3 entire orders of coral. On land, 75% of species perished. Those lush forests were wiped from the face of the Earth, along with many of the creatures who called them home. But why that volcanic eruption caused such a catastrophic extinction is still a bit of a mystery. Many scientists think the greenhouse gases directly from the eruption just aren't enough to cause such major environmental shifts across the planet. Some think the magma erupted through massive coal beds, igniting them on its way to the surface. This would have released way more greenhouse gas than the eruption alone. But in 2014, researchers stumbled onto a suspicious clue. It didn't look like the mark of a volcano, but of something rapidly multiplying, something alive. It all starts with the element carbon. It has a number of isotopes, which is what we call the lighter or heavier versions of its atoms. These isotopes record a sort of fingerprint of the ancient carbon cycle in Permian-age rocks. At the point of the extinction, Earth's carbon cycle was thrown out of whack through the sudden appearance of many lighter carbon atoms. But the researchers noticed this didn't happen through a series of episodes, which is what you'd expect from volcanic eruptions. Instead, the pattern of disruption was exponential, the kind of pattern we see in living things. So they put together a hypothesis. This story starts with a tiny organism getting a massive upgrade. Sometime around the end of the Permian, give or take a few tens of millions of years, a single horizontal gene transfer occurred. Horizontal gene transfer is when genetic material moves between organisms that aren't parent and offspring. It happens a lot in things like bacteria, for instance. Somehow, genetic material from a bacterium in the class Clostridia ended up inside an archaea called Methanosarcina. This gave Methanosarcina the ability to more efficiently perform methanogenesis, converting organic carbon to methane and generating energy for itself along the way. From the perspective of the microbes, this upgrade occurred at the best time possible. But for anything else living on Earth, it was a perfect storm. Oxygen in the oceans was already low in the late Permian. These conditions allowed a massive amount of organic matter to build up, a microbial feast. On top of that, volcanic carbon dioxide and warm conditions made microbes grow faster. But they couldn't dig in just yet. They were missing one key ingredient. Methanogenesis relies on the presence of the metal nickel. And for the last couple billion years on Earth, there just hasn't been much nickel in the oceans. Today, one of the world's largest nickel deposits can be found in Siberia. It formed during that big volcanic eruption at the end of the Permian. So you might be able to see where this story is going. If the eruption brought all that nickel to the surface, it could have rained the secret ingredient for methanogenesis across Earth's oceans. And indeed, when the researchers looked at Permian-age rocks in China, they found a sudden spike in nickel just before the extinction. So Methanosarcena, who had just unlocked a new ability, had all the ingredients needed to use it. And methane is an extra potent greenhouse gas compared to carbon dioxide. It warms the planet 28 times more. This set off a chain reaction. Emitting methane warms the planet. This warming makes microbes grow even faster, causes the oceans to acidify, and robs them of even more oxygen. Other microbes that thrive without oxygen convert methane to hydrogen sulfide, an extremely toxic gas that could have even spread to the land and poisoned animals there. As more species die, the methanogenic microbes get even more material to feed on and release more methane. And all this put together was just too much for the inhabitants of the Permian Earth. The extinction brought the Permian to an end and marked the beginning of the Triassic period. Exactly how much of a role microbes played in this extinction is hotly debated by scientists, and is very much still an area of active research. But regardless of if they were to blame, microbes certainly benefited from the extinction. Imagine you're a geologist looking at a rock face of sedimentary layers that record the Permian-Triassic boundary. At your feet, you see the carbon-rich coal beds of the Permian, a result of all those lush forests. But moving upwards, those coal beds end abruptly at the boundary. This is the beginning of the coal gap, a time that records the absence of large amounts of vegetation on Earth. Within this gap are fine-grained rocks like mudstones and carbonates that have very little organic matter. These are called microbialites, fossilized microbial mats that dominated the planet for 3 million years. Microbialites are actually pretty common in the oldest rocks on Earth, from the time before more complex life evolved. You might have heard of stromatolites before. They're a type of layered microbialite. But once creatures showed up who liked to graze on all that algae and churn up too much sediment, microbialites basically disappeared. So their return in the early Triassic is evidence of the lack of more complex life. In this case, these microbes, including cyanobacteria, are known as disaster taxa, something that flourishes immediately after a catastrophe. And geologists see this pattern of microbes flourishing after multiple other mass extinctions too. All this evidence from Permian and Triassic rocks reveals the next chapter of our story. After the extinction of those massive Permian forests, there were no more roots to stabilize the soil. More nutrients washed into rivers and lakes, fertilizing blooms of microbes. On top of that, the warmer temperature made the microbes grow even faster. The early Triassic became a microbial playground. It took a long time for many complex ecosystems to recover after the Permian extinction. Most took over 5 million years. Some scientists believe these microbes delayed the recovery of larger life. They choked freshwater ecosystems, used up oxygen, and released toxic chemicals. Other researchers take a more favorable view. They think the microbes could have helped recovery after the extinction. Fossilized microbialites aren't completely devoid of bigger life. In fact, they provide a refuge for small crustaceans. The microbes supplied a limitless buffet and layer of oxygen and water that was otherwise devoid of it. And photosynthetic cyanobacteria would have helped pull carbon dioxide out of the atmosphere. Even today, they are responsible for 25% of photosynthesis in the ocean. Of course, the Earth and life on it eventually did recover. After all, you and I are here now. But during the extinction, carbon dioxide in the atmosphere went up by a factor of 6 in 75,000 years. And on our current trajectory of human greenhouse gas emissions, we will emit that much in just hundreds of years. And blooms of microscopic algae and bacteria are becoming more frequent because of warming temperatures, deforestation, and nutrient runoff from agriculture. While a massive volcanic eruption hundreds of millions of years ago isn't the same as our emissions today, there are lessons to learn from the end Permian. One of which is that the smallest life on Earth can have a big impact on the rest of us.
We are so excited to tell you about our new TV series, Eons, Life and Death on Pangaea. We've been working on this for the last few years, and it's finally ready. The 6-part series, set in the Permian period, tells the story of the formation of Pangaea, when life, unlike anything seen today, was flourishing. But it was a time that ended in tragedy, with the most catastrophic mass extinction in our planet's history. It's free on PBS platforms, including the app. Check out the link in the description for more on where to watch.
Also, thanks to our small but mighty group of eontologists.
Addie, Amanda Seabach, Annie and Eric Higgins, Benjamin Birdsall, Carl Wolfel, Jackie Scott Rouston, Jake Hart, John Davison Ng, Juan M., Melanie Lamb Carnevale, Nico Robin, Raphael Hasse, Tony Dye, Victor Ankiko, and Steve.
By becoming an Eonite at patreon.com/eons, you can get fun perks like access to behind-the-scenes content, including clips from Eon shoots. And as always, thanks for joining me in the Annie and Eric Higgins studio. Subscribe at youtube.com/eons for more evolutionary escapades. Somehow, genetic material... Sorry. I just had a Star Wars moment. I was like, somehow, Palpatine returned. Midichlorians.